for the midterm, it's fair game for the final. If it was not important enough to be on a midterm, so we saw it before, but didn't make it to a midterm, it's not important enough for a final. So you can expect things like black body radiation, interpret wave functions, uncertainty. You could expect nuclear physics topics, stuff like that. The other stuff, quantum wells, for sure. What else? The Bohr model. The Bohr model is important because it's the simplest model that gives amazingly good results. It's hard to find a model that simple yet that accurate anywhere else in physics. Quantum wells, Bohr model. Or the boundary conditions for the wave function. That could mean barriers. So reflection problems like we had on the midterm. That could mean quantum wells. That could mean that just like on the homework, you had to set up something with a quantum well and figure out whether the condition was a tangent of Ka equals Ka or whatever it was, something like that. Tangent of Ka equals K over kappa, something like that would be fair game. And of course, nuclear physics. What questions do you have so far before I go into some longer examples? I'll probably give you a minute to look through your notes and come up with questions while I go through stuff to figure out if there's anyone here who I have to give stuff back to. I don't see Amanda. Is Daniel Kim here? Is David Siegel? No. I don't see Martin Serrato. Is Baron here? Two basic things. Well, first of all, do you have any questions? Yeah.
The reactions that we deal with, are they going to be all relativistic or non-relativistic, or are you going to specify?
I'll generally let you know. A good rule of thumb is that the least massive particles are more likely to be relativistic because you don't have to give them that much energy to get them going really fast. So like the electron emitted in a reaction could be relativistic. The recoil of the nucleus, because it's tens of thousands of times more massive than the electron, much less likely to be relativistic. But when in doubt, just assume that this is by definition true. The Ke is mc squared plus Pc squared minus mc squared. That is always true by definition, and this is roughly equal to p squared over 2m if or Pc is much less than mc squared. Other questions? Alright, so here's a question for you. Nuclear physics, where's the eraser? Turns out that One fun thing about teaching nuclear physics is that since I don't work in a field that uses it, I always get to look up some cool trivia and learn a little detail. One thing that turns out to be true is that deuterium burns at a much lower temperature than protons, by which I mean that, remember how on the homework you just turned in today there was that chain of reactions with, that goes from hydrogen to helium-4? Well, some of the steps in there are much easier than others. I just listed 3 or 4 steps in a row. Some of them are much easier than others. It turns out that one of the easiest steps to accomplish is this one. This is the easiest, this is one of the easiest steps. So it can happen in brown dwarf stars. It can happen, I understand that some people don't classify them as stars. I'm not an astrophysicist, so don't ask me what the appropriate classification is. But it can happen in much less massive, much lower temperature objects. So one thing that we could ask is, if we had this reaction, if I told you the amount of energy that the brown dwarf was putting out, and I told you the mass defect, the mass defect of the reaction, and the energy output of the brown dwarf, could you figure out how much helium-3 is produced per second? First of all, are there any other products from this fusion reaction? Because I'm obviously not going to give you exactly the brown dwarf problem. It would be perfectly fair to give you a reaction and ask if there are any other products from that reaction. And just by using conservation laws, you should be able to figure out yes or no. You might not be able to figure out if there's a photon produced, but you can at least figure out if any charged particles or neutrinos are produced. Are there? Well, there's only 2 possible answers, yes or no. So take a moment to think about it, and then we'll vote. Because democracy always works. Or at least that's what progressive educators tell me.
No, it doesn't produce any other.
Well, no, we're going to vote on that. You're not going to answer yet.
That's a dictator.
For now, that's just like your opinion, man. And we will figure out. Okay, how many say that there are other products? Let me say there aren't. Good. Mass is conserved because initially we had a neutron and a proton and another proton, and we still have 3 baryons. Charge is conserved because we had 2 protons, we still have 2 protons. Now, how will we figure out from the mass defect the energy output of the brown dwarf? From the mass defect and the energy output, how to figure out the helium production rate?
The mass defect is the total amount of energy needed or required to make the helium, I believe, right? So then we.
Is the energy required to be put in?
Well, because it's the kinetic energy of the 2, the deuterium and the helium.
No, if this fusion reaction required an energy, a net input rather than a net output, the brown dwarfs would not be doing it spontaneously.
Okay.
So what happens is that the only other thing that's produced is kinetic energy. And you can figure out how much kinetic energy is released, how much extra kinetic energy there is, by looking at the masses of the reactants and the mass of the product. Just add up MC squared for all the products and subtract off MC squared for all the reactants. And that is the energy released. It's that simple. If the products had more mass than the reactants, then these fusion reactions would only happen if you were able to first accelerate the things to really high velocities, and then they would actually, the products would be unstable because the system would have lower internal energy, less potential energy if that nucleus broke up. That's practically the definition of an unstable nucleus. One where the mass of the products after the decay is less than the mass of the nucleus before the decay. And the definition of an exothermic nuclear reaction is one where the mass of the reactants is larger than the mass of the products. Because things only happen spontaneously if they release energy rather than taking energy as input. All right, this is, I mean, frankly, even biology, although biology might not look spontaneous, even biology is all about spontaneous reactions. The fact is that sugar is going to have lower energy if some oxygen reaches it and breaks it apart. If you can break apart some sugar when oxygen reaches it, then there will be lower energy afterwards than before. The potential energy stored in those chemical bonds of the CO2 and water that you get out of burning sugar will be less than the potential energy stored in the bonds of the sugar. So it's only because when oxygen reaches sugar that there is a spontaneous reaction. That's how we're alive. All of the non-spontaneous stuff, all of the effort in biology is us finding the sugar, us inhaling the oxygen, and then all of that oxygen and sugar being brought to the right places in close proximity with each other for the reaction to happen. That's all the work of bringing them together. But once they're together, it happens spontaneously. Spontaneous reactions lower energy. So, how are we going to figure out how much helium-3 a brown dwarf is producing each second? Yeah?
You take the amount of energy per reaction and then do some math with the output.
Do some math. Okay, so if you just write, and then I do some math on the test, I'll give you a couple of points. What is that some math that you would put on your test paper?
You divide the energy output of the brown dwarf by the energy released per reaction.
Something like that would be totally fair game. Or something where I give you another reaction and I say that this reactor is producing this much energy per second. Maybe I give you the reactions involved in the fuel cycle of a nuclear reactor and I say it's producing this many megawatts. How many neutrinos per second are produced? So you'd have to look at that reaction and figure out, okay, every time we get a reaction, we produce this many joules from the mass defect, and I'll give you some information for that. So, well, I'll make it a little more concrete. Neutron N10 plus, I don't have the fuel cycle of a nuclear reactor memorized, so I'm not going to start writing down wrong things. Plus XAZ yields Y. And I might give you this here, and then you have to figure out what else is produced. And I might tell you you might have to figure out if neutrinos are produced or how many neutrinos are produced. That will be a totally fair calculation. And one thing you might notice is that a lot of what we're doing looks similar to chemistry not just because I've got reactions with chemical symbols and arrows, but like converting these rates, it's almost like stoichiometry calculations, in chemistry to figure out what your percent yield was. You figure out, well, if I had this many moles of this reactant and that many moles of that reactant, then I should be able to convert that into however many grams of product. And so you do calculations, a lot of multiplications like that. It basically is chemistry. So even if you never again deal with anything radioactive in your career, if you do something related to material science, which many of you will, then you will probably deal with some chemistry. What I like to say in physics is I'm less interested in whether you know the topic than in whether you know how to do the type of calculation, because it'll show up elsewhere. So that would be fair game for nuclear physics. I give you some reaction, I tell you to fill in the blanks with what else is produced, and I give you some amount of information on the energy output, and then I ask you for the rate at which products are made, or maybe I tell you the power output. Maybe I tell you the power output and some information on how much fuel is consumed, and you have to figure out the energy released per nuclear decay or per nuclear reaction. That would be fair game. Questions? No questions? I could give you problems with radioactive decay and half-life. And in radioactive decay, there's two basic things to know. These are the two basic things to know. The rate of the decay is just equal to the amount there times constant 1 over the lifetime. And the amount present, you can either write it as an exponential with e or as an exponential as a power, you can write it as a power of e or a power of 2. They're both valid. It's just, this is better for calculus. This is better for thinking about numbers. That should be a minus t, not a t with a very large thing on it. Yeah.
So on the homework, we got the probability of a decay,
Yeah.
like per minute. How do we fit that into the equation?
The probability of a decay per minute. Let me look at that problem. Not sure. Oh, okay. A nucleus has a 0.05% probability of decaying in a minute. Got it. So, if I had, good question. .05% or 0.0005. So that means that the probability that it will not decay is 0.9995, right? So if I let it sit for 1 minute, this is the fraction of stuff that will still be remaining. N of 60 seconds is equal to n of 0 times 0.9995 is equal to n of 0 e to the minus 60 seconds over tau. It's also equal to n of 0 2 to the minus 60 seconds over the half-life. Does that help? So now you have the information needed to solve for either tau or the half-life. Questions? I see people writing, so I'll pause. I suspect that someone must have a question about that. Anyone? Anyone? Bueller? You? Some of you have actually seen that movie. Wow.
Classic.
I actually met Ben Stein. I won Ben Stein's money on his TV show. He had a game show back in the early 2000s, and I won $850 of his money. But
And what was the game show?
what?
What was the game show?
It's called Win Ben Stein's Money. It was like Comedy Central. It was like Jeopardy, sort of. You know, 3 contestants answer questions, win money, but it's elimination style. So first round, 3 people. Person with the least money goes away at the end of the first round. Second round, 2 people and Ben. So you know how in Jeopardy, like you're piling up money as you go through the rounds? Well, Ben is there to pile up money so that you don't. And Ben has been playing that for years. He has that buzzer down. He knows exactly how to press that. His reflexes are perfect. So basically, you only get to answer the questions that Ben gets wrong, because he will buzz in first. Then they eliminate someone. Then the third round, they give you 10 questions, they give Ben 10 questions, and you're guaranteed to get what you went into the round with. If you beat him, you get $5,000. If you tie him, you get what you went in with plus 1,000. And I missed the math question. So I would have tied him if I got the math question. The 2 angles that add up to 180 are said to be what?
Supplementary.
So it's either supplementary or complementary, and I guessed complementary, and it turns out to be supplementary. Anyway,
So he's a pretty smart guy.
he got that one wrong too. He got some other ones right. All right, so questions about nuclear physics. Those I could beat Ben on. Me versus Ben on nuclear physics, yeah.
So for that, you just take like log base 2 to find the half-life, right?
Yeah, or you could take, you don't have to take the base 2 log. So I could say that ln of 0.9995 is equal to ln of 2 to the minus t over the half-life is equal to minus t over the half-life ln of 2. So the half-life is equal to minus 60 seconds ln 2 over ln of 0.9995, which is going to be roughly, well, let's see here. The ln of 1 plus x is roughly x. That's just a fact of Taylor series. So here x is minus 0.0005. So it's going to be minus 60 seconds times ln of 2, which I think is 0.7 or something close to it, over minus over minus 5 times 10 to the minus 4. Is I think. And no, I will not expect you to memorize that Taylor series or the natural log of 2. I was just trying to get an estimate in my head. About 12 times 0.7 is roughly 60 over 5 is 12 times 0.7 is, about 0.7 is about 9. So 9 times 10 to the 4th seconds. Other questions? Yeah.
This is not about this, but do we have to memorize the lepton numbers?
Yeah, you should know that electrons and neutrinos have lepton number +1, and positrons and antineutrinos have lepton number -1. If you don't know the lepton numbers, then you can't figure out whether or not a neutrino was produced. And neutrinos are really, really important because frankly, they're the only directly experimentally observable thing in particle physics where we absolutely know that there is some other physics beyond the standard model. Everything else, we know that the standard model works too well. If you follow physics news and physics blogs, every few months you'll see that people at the LHC or at some other particle accelerator have found an anomaly, a statistical anomaly that doesn't quite match the standard model, but it's not yet statistically significant. The results are slightly different from the standard model, but they're not statistically significant, which means that they're not different from the standard model. But maybe they will be with more data. And stay tuned to find out. And then a few months later, nope, that anomaly went away. It's like a TV show where they keep hinting that they're going to throw a plot twist at you, and then they don't. It's like watching Lost several years ago. So they keep saying, oh, well, maybe there's this anomaly, maybe there's that anomaly, and it always goes away. The peak of that was December of 2015. Did you hear about the diphoton bump, the 750 GeV bump? They thought that they found evidence of some huge massive particle with mass of like 750 giga-electron volts, 750 proton masses that decays into 2 photons, completely unexpected. It was always just a little bump in the data. There were hundreds, a bump that could be noise. Hundreds of theory papers were written explaining this. 6 months later, they get enough data to say that, maybe it was 8 months later, they get enough data to say, no, it's just noise. Right? That's how desperate people are for a new effect. And neutrinos are the one place where we absolutely know that there's something else. Because neutrinos turn into other kinds of particles, which means that besides what they call the left-handed neutrinos, there must be right-handed neutrinos. There must be neutrinos where the spin and the linear momentum point in the same direction, and they must have some kind of unknown properties. There's something in there that isn't in the standard model. Who knows what? So that's why neutrinos are important, because they're the one area of particle physics where we actually know that someone's going to make a discovery someday. God only knows when. The thing about neutrinos that makes them so hard to detect is that if you know how I said that the way they detect neutrinos, they just basically put a giant detector there and wait for them to bump into something and cause a nuclear reaction? Hardly any do. The overwhelming majority of neutrinos just pass right through the Earth. If you had a lead shield that was 1 light year thick, only about half of the neutrinos would be stopped. That is how weakly they interact. That you could have a light year's worth of material and only half of them would hit it. So that's why it takes forever to do these experiments. All right, other questions? Then I've got an example for you to work on. I'm not going to ask you to do anything on the final that would require Mathematica, but I could ask you to at least derive the equations for a quantum well. So, quantum well, V equals V naught, V equals 0, X equals plus A over 2, X equals minus A over 2, X equals 0. Second excited state. Come up with a condition involving K kappa A in the tangent function. Basically derive one of those equations that we derived in class. You don't have to plug it into Mathematica and find the solution. That would be way more than you can do during the final. Just come up with a condition. So, do it. Talk to each other. You should probably start by figuring out whether that wave function is a sine, a cosine, or a mix of the two. So, talk to some people, figure out which of those it would be, and then come up with a condition. I'll be back in a few minutes. Symmetric. Now that doesn't mean that psi squared is symmetric, so the square root of psi squared could either be even or odd, but psi squared has to be even. So then, given that it's a cosine, you have to figure out what sort of condition it obeys with the K kappa A and the tangent of something. Obey at the boundary of the quantum well. What things are continuous?
The position and the derivative.
The position is continuous? What is the position?
Well, they have to hit the same
What?
place.
The position of psi? What's the position of psi?
They have to equal 0.
The position of psi has to equal 0?
No, okay.
Covfefe. It makes about as much sense.
Yeah.
Psi has to be continuous at the boundary, and what else?
The derivative is.
Yep. Yep. Okay, so now based on those two conditions, you should be able to do the algebra to work things out, because you're going to get that inside psi is A cosine kx. And out here, psi is B e to the minus kappa x.
I no longer have TV or regular internet. I look out my window a lot.
Excuse me, Professor.
Watch the squirrels.
I don't want to interrupt his.
Yeah.
You hate the outside.
No, but he lives in an area
Yeah.
lots of activity.
It's like flying insects.
Yeah.
Like bears.
Excuse me, Professor. What would a mixed wave look like?
A mix of sine and cosine would either be for a case where there's three possibilities. One, the way the quantum well is not symmetric. All right, like maybe the potential's higher on one side than the other. That's one possibility. Another possibility is that it's a superposition of, say, a ground and excited state, so that you have the sum of the sine and cosine. And then the final possibility is that you made a dumb choice of coordinates and you put your x equals 0 on the edge of it. So now you have a wave function that's symmetric about the center but might not be symmetric about, physically it's symmetric about the center. Okay, the laws of physics don't know where you decided to write down x equals 0, and frankly they don't care. So physically it's symmetric about the center. You want to put your origin in such a place so that symmetric about the center is also symmetric about the origin, because then it's easier to write down equations. But we could always, what I'm about to write down will not be on any test. But you could always put your origin somewhere other than the middle. So according to the laws of physics, then if this is our case, here's x equals 0, we're still either going to have sine of k times, this is now a over 2. X minus a over 2 is our distance from the center of the quantum well. We still have a function that is symmetric about the center, so it's going to be an odd or even function of x minus a over 2. It's going to be an odd or even function of the distance from the center. That's all that physics says. Physics just says that your state has to be even or odd about the center, so it's an even or odd function of your distance from the center. But sine of k times x minus a over 2, if I want to write this in terms of sines and cosines of x, well, now I have to use some trig identities. So, like, let's see here. This is going to be sine of kx cosine of ka over 2 minus cosine of kx sine of ka over 2. Right? It's still an odd function of the distance from the center. That's all that the laws of physics care about. But you put your origin somewhere else, so it's the symbols that you write them in have just become a lot more complicated. But that's not going to help us solve this. Let's try to solve this. If we solve this, well, we have to match psi. So that means that a cosine of ka over 2 is equal to b e to the minus kappa a over 2. And then we've got to match the derivative of psi with respect to x. Derivative of cosine is minus sine. So minus k sine of ka over 2, sorry, that should be minus k big A, is equal to minus kappa b e to the minus kappa a over 2. Or a sine of ka over 2 is kappa over k b e to the minus kappa a over 2. So we've got this and this. Now what do we do?
Divide.
Divide them, yep. So I'm going to take sine over cosine, I'm going to get tangent, I'm going to cancel out the big A's. Tangent of ka over 2 is equal to kappa over k. Now, what if I asked you to write that, or at least I asked you to write the right-hand side in terms of the particle's energy and the potential V naught? Now what do you do? So I asked you to write this is the particle energy E and the potential height V naught, because the particle has some energy E less than V naught. So how are kappa and K related to E and V naught?
That's a kappa is, no, k is equal to the square root of e minus v naught.
Does that look familiar? Or, so I could could always ask you to write it that way. Again, you have to get used to solving these kinds of equations, because if you can solve these kinds of equations, besides being able to do more advanced quantum, you can do fiber optics, you can do waveguides, you can do a lot of things in physics. The book that I go to is my go-to guide for quantum wells, is also my go-to guide for white waveguide theory, because it has both, because they're essentially the same math. And not only are they the same math, they show up in the same application area. Quantum well lasers, that are made, you can make a quantum well laser where you just send an electron from one level of the quantum well to a lower level, it emits a photon, and then that light gets trapped inside of a waveguide where it bounces back and forth between two barriers way out here. So the barriers aren't in here, the barriers are much further out. They're separated by the wavelength of light, which is hundreds of nanometers, rather than the wavelength of the electron, which is maybe angstroms or nanometers. But it's the same math. The math of a waveguide is just an electromagnetic wave bouncing back and forth between two mirrors. Those mirrors are made of dielectric materials with different refractive indices. And so you wind up matching values of the electric field and the derivative of the electric field at an interface. But it's all exactly the same. And that's why my favorite book on waveguides is also my favorite book on quantum wells. Questions? Yeah.
Now, when it comes to the excited state, your K value is going to be, what was it, your N pi over L? Or A over
That's
S?
only for an infinite square well.
Okay.
All right? This is not an infinite square well. Psi is not equal to square root of 2 over L sine pi n x over L, or over the width A. That's only for an infinite square well, because for an infinite square well, what you get is that psi is 0 at the edges. But here, once we go out into this disallowed region, it's not 0, it's e to the minus kappa x, which is small, but not 0. That's the difference between this and this. Here, if we think of kappa as being defined by this equation, h bar squared kappa squared over 2m is v naught minus e. What if v naught's infinity? Then what's kappa? Don't overthink it. Infinity. What's e to the minus infinity times x? What's e to the minus infinity?
No, it's 0.
E to the minus infinity is negative infinity? No, what's the exponential function decay to at infinity?
0.
0. So yeah, so out here the field is 0. And here, the wave is 0. And here the wave is not quite 0 yet. It's close to 0. Decays towards 0 really fast, but it's not exactly 0. That's the difference between this finite quantum well. When I say finite, I mean that the barrier height is finite, and the infinite square well. The larger the barrier height, the larger kappa, and so the faster e to the minus kappa x decays. So the larger the barrier height, the closer this gets to 0. But it's not actually 0. Does that make sense? Other questions? For black body radiation, pay attention to the scaling of those curves, because the ability to handle scaling relationships like that shows up in a lot of physics in a lot of places. So like just knowing that curve in general has this form. RT of nu is proportional to nu cubed over e to the h nu over kBt minus 1. This is tremendously complicated, but at the peak, if you just know that, then you know that no matter what the temperature is, this denominator is, no matter what the temperature is, this denominator has the exact same value at the peak for all temperatures. Because whether I'm at a millikelvin, a temperature that people can easily cool to, or I'm at the center of the sun or the center of a supernova, h nu peak over kT will be, I think, about 2.8. And that's as true in a nanokelvin experiment in the lab as it is at the center of a supernova. H nu peak over kT is about 2.8. So all bets are off as soon as you go far away. Everything's tremendously complicated. But if I just asked you what the peak depends on, and I would mostly ask you about the peak, not just because the math is simple, but because it's what people look at. People, how do we know, well, now we have a lot more information. Before they landed people on the moon, how did they know the temperature of the surface of the moon? How do you think they knew the temperature? They pointed an infrared camera at it and looked to see where the peak of the spectrum was. That's how they knew the temperature on the surface of the moon. All right? How do we know the temperatures of stars? We point spectrometers at them and look to see where the peak is. For that matter, people do thermal imaging sometimes in medicine. They point a spectrometer at the skin and look to see what the temperature is. All right? It's all, so the peak is practical. Okay? The peak, I'm not just going to ask you about the peak as opposed to the other parts of the curve because, well, the peak is where the math is easy. It's because it's practical. So get these relationships down, that the intensity at the peak is only proportional to nu cubed. Because knowing where the peak is will tell you what the temperature is. Knowing how high the peak is will tell you what kind of camera and sensitivity you need. Okay? If the peak is really high, then you don't need a camera with high sensitivity. If the peak is really low, then you do need a camera with high sensitivity. So know those scaling relationships for the peak. Know that the peak is proportional to nu cubed. Know that the area under the curve is proportional to t to the fourth. Know that the peak nu is proportional to t. Just know stuff like that. It gets you a long way in analyzing data and designing experiments. That's all I have to say. I'm not going to kick you out. I'll just hang around up here for a few minutes. You can go through your notes, figure out if you have other questions. Leave when you want to. Ask questions as you want to. Make sure you turn in your homework before you leave.
So one's wrong. She was.